Hello everyone. We shall continue our discussion on Hartnell governor, and probably in today's lecture I'll be able to solve a couple of problems on Hartnell governor. I hope you already have those problems and you have written them on paper, and I hope you all are ready with your tools, that is at least calculator and pen, paper. I hope you are ready. But before I really take up those problems, I have a couple of terms to introduce you. I wish you to introduce a couple of terms and also explain the significance of those terms. And these terms are quite common in the numericals. Okay, you all know that Hartnell governor has bell crank levers, two of them in fact. Okay, one on either side. Bell crank lever, as you all know, it has two arms, and in our case the bell crank lever angle between the two arms happen to be 90 degrees in our Hartnell governor, and we have called those two arms as ball arm and sleeve arm. Okay, we have, and so it looks something like this. Okay, this is the spindle axis, and say this is the fulcrum, and say this is the ball arm, and perpendicular to this is the sleeve arm. Okay, this is the normal position, and the ball arm is the parallel to the axis of the spindle. This is the normal case. But depending upon the speed of this, the speed of the governor, the spindle, and the rotation of these balls, these balls or this arm may go like this or may go like this, depending upon the speed. And the same figure, the next sketch I have drawn for, say, assuming that the ball arm has gone away, deviated, and the speed has increased, and maybe something like this. This is possible, and also this also is maybe possible. Another possibility is the speed with respect to this has decreased. In that case, the ball arms may come towards the spindle axis, and therefore it may happen something like this also. So these are the ball arms, this is the ball, and the sleeve arm is like this. Okay, so these are the different possibilities of position of the bell crank lever, maybe like this, or maybe like this, depending upon the speed of the governor. Okay, all these possibilities. So now I would like to, with respect to the spindle axis, the ball arm is making certain angle for agree angle. Okay, the same is the sleeve arm also. Okay, sleeve arm will follow the ball arm because the angle between the two arms is always 90 degrees, and I shall only refer to the ball arm. The ball arm is making certain angle with the spindle axis. Similarly here also the ball arm is making certain angle. If then we say that with respect to this position the ball arm is oblique. Okay, so therefore if we say that the ball arm is oblique here, the ball arm is oblique, and I shall refer something what is called as obliquity. Okay, this is a measure of obliqueness. Okay, so measure of obliqueness, and we are not going to in detail about what is how much is the obliquity, etc. But whether it is oblique or not, if it is making certain angle, then I say that this is oblique, this also is oblique. And obliquity I shall introduce, and I say that the obliquity is 0 in this case because the angle between the ball arm and the spindle axis is 0, and therefore obliquity is 0. But here obliquity is non-zero, it is not equal to 0. And similarly here also the obliquity is not 0. So obliquity is not 0. Okay, so obliquity in the three cases I have just written here. Okay, so whenever the bell crank lever, either it is like this or like this, we see that the bell crank lever is oblique. We have oblique. Okay, now what is the effect of this? Okay, on our moment equations. Let me come back. Say, let me show the forces that are acting on a different. Say this here, the speed let it be omega, and let the speed here be omega 1, and let the speed here be omega 2. Definitely omega 1 is greater than omega and omega 2 is less than omega because the ball has come inwards. Okay, so now what are the forces? The centrifugal force, as we know, it is mv into omega square into r. And I also have the weight of the ball, that is mv into g, and probably here ms into g. Sometimes ms is 0. In that case, you have only spring force plus s divided by 2. So these are the different forces, and I will be taking the moment about the fulcrum, and when I take this weight is passing through this, and therefore I have moment due to only two forces. So if I write down the equation, ms into g plus s divided by 2 into a is equal to mv into omega square r multiplied by b. So this is the moment equation in the first case. In the first case, this is the moment equation. Okay, so here, what are the forces that are acting? Let me write down. Say this is mv into omega 1 square and r1. R1 is the radius of rotation. And the weight of the ball, okay, so mv into g only, but remember, this line, the line of action of the weight is not passing through the fulcrum, and therefore there is some scope for momentum. So this also will produce moment. And the spring force and the mass of the sleeve or weight of the sleeve, that is ms into g plus, since I am taking this as position 1, I shall call it as s1 divided by 2. Okay, now this, all the three forces have moments. Please remember, here though I have three forces, one of the forces doesn't have any moment, and when I write moment equation, I have only two moments. But here I have three moments, three forces, and all three moments mv into omega 1 r square r1 multiplied by b1, and this ms into g plus s1 by 2 into a1, and mv into g multiplied by this r1 minus r. So that means I have all the three. That's what. But sometimes, okay, you are asked to neglect the obliquity. Okay, so as if this is not oblique. So in that case, what you have to imagine, as if it is here oblique. So neglect obliquity, as if don't consider the effect of obliquity. That is what is stated in the problem. So in that case, you don't have to consider about this, and in that case it is as well as this. That case b1 is equal to b and a1 is equal to a, and in that case mv into g will pass through this, and therefore you will not have the moment due to the weight of the ball. There is another way of telling this neglect obliquity is, don't consider the moment due to the weight of the ball, or in other words, gravity effect of the ball has to be neglected. Okay, so in that case, if I neglect the obliquity effect, if I don't neglect, you already know ms into g plus s1 by 2 multiplied by a1. This is anti-clockwise moment. Then mv into g multiplied by r1 minus r plus mv omega 1 square r1 multiplied by b1. This I have already shown you. Okay, that is when you don't neglect the obliquity effect. But I have to neglect the obliquity effect. In that case, the expression is going to be ms into g plus s1 divided by 2 multiplied by a is equal to then mv omega 1 square r1 multiplied by b. This is how the equation is going to be. So whenever you neglect the obliquity effect, then you have the moments due to only two forces. Okay, third force is not going to be there. And similarly, if I neglect it here, this is ms into g plus s2 divided by 2 multiplied by a is equal to mv into omega 1 square not omega 1, it is omega 2 square r2 multiplied by b. Okay, this is how the equation. So in that case, so whenever you neglect the obliquity effect, then you don't have to calculate a1, b1 or a2, b2 like that, and therefore the analysis becomes much simpler. Okay. So depending upon what is stated in the problem, so then accordingly we have to act. Okay. I hope this is clear to you, and now we are ready to take up the problem. Okay. Please take up the problem and keep on reading, and I also will join you reading, and we shall both read it together and write down the data given in the problem. So again, I should not solve it completely and write down what is the numerical value. I don't want you to copy my value, whatever I get. Okay, whatever I write, I want in fact you to calculate on your own. Doesn't matter, you can take few minutes extra, and then we can so that you will be able to get confidence in solving, and you can solve any number of problems. I shall be demonstrating and with you to solve a couple of problems only, and many more I shall give you as assignment, and you will be able to solve them. I hope. Okay, let us read it now together. Okay, sentence by sentence, and then whenever we are able to understand and write down the data, I shall complete it there, then and there only. Okay, the first sentence. The mass of each ball of a Hartnell type of governor is 1.4 kg. Okay, the matter is quite clear, we are able to understand. The mass of each ball is 1.4 kg. So I shall write down the data. MB, this is equal to 1.4 kg, quite clear. Okay, next sentence. The length of ball arm of the bell crank cleaver is 100 mm, whereas the length of arm towards sleeve is 50 mm. I think again the very clear, no confusion, nothing. We know that the ball arm is 100 mm. The ball arm is denoted by B, so 100 mm. So as and when I require to convert it, and in meters I shall do it. 100 mm multiplied by 10 raised to minus 3. Now I shall write it in millimeter only. And similarly, the sleeve arm, say A, I am calling it, and this is 50 millimeter. Okay, the distance of the fulcrum of bell crank lever from the axis of rotation is 80 mm. Again, full stop. Okay, quite again it is quite clear how with our notation. The distance between the fulcrum of the bell crank lever from the axis of the spindle is, we are calling it, denoting it by C, and this C is 80 mm. Okay. The next, the extreme radii of rotation of the balls. Quite clear here. Again, the extreme. What do you mean by extreme? Minimum and maximum. Okay, minimum and maximum, they are being referred as extreme. Extreme radii of rotation of the balls are 75 mm and 112.5 mm. Okay, so now for this 75 mm is definitely the minimum radius. R minimum is 75 mm and R maximum is equal to 112.5 mm. Okay, I have continued to write them in millimeter, but be careful while substituting. Okay, so whenever it is required, I shall change it to meters. The machinery, the maximum equilibrium speed is 6%. Okay, the maximum equilibrium speed is 6% greater than the minimum equilibrium speed, which is 300 rpm. Okay, so though it has been slightly twisted or not twisted, but you need to carefully read and understand. Okay, there is one speed 300 rpm. The sentence starts with maximum, but you have ended with 300 rpm. But maximum speed is not 300 rpm. It is said that the maximum speed is 6% more than minimum speed, and minimum speed is 300 rpm. So here, N minimum and it is equilibrium speed. What is the meaning of equilibrium speed? Without considering friction. That is the meaning of equilibrium speed. So here minimum is 300 rpm. But in nowhere in our expression, I need later on, not in this unit, I need what is called as omega minimum, and therefore please convert this in so many radians per second, omega minimum. Okay, this is a must. Okay, and I also know what is omega maximum. So I can find out what is N max and then omega max. I can straight away do omega max. Omega max also is 6% more than the minimum speed, and therefore it is 1.06 times omega minimum. 6% more than omega minimum. So therefore it is 1.06 times minimum speed, and please get this value also. So many radians per second. Okay, so I have a lot of data here, and now still, okay, now I have come to determine the stiffness of the spring. Okay, what is asked I can find out. So I have denoted the spring stiffness by K. K is what? Okay, K. K may be Newton per meters or Newton per millimeter, etc. In whatever units you find out, you can express it, and I can only say that the first thing what is asked is what is K. This is the first thing. This is not the only thing what is asked in the problem. Then equilibrium speed, of course, without taking friction force into account, when the radius of rotation of the ball is 90 mm. Okay, the second case, second one is R is equal to 90 mm. What is N? Or what is omega? Of course, first we will find out omega, and then you can convert it and express the speed in terms of RPM, and this is what is asked in the problem. Okay, so if you have any doubt, this is all data what of case. Of course, one more very important sentence is there: neglect the obliquity of the arms. Okay, neglect the obliquity. This is very important. Neglect obliquity. So in the entire solution, while solving the problem, we shall assume that obliquity effect is to be neglected. Okay, that means whenever I write down the moment equation, moment balance equation, I shall have only two moments. One moment due to centrifugal force, the other moment is due to the forces on the sleeve. And I have one more information here. What is MS? And what is MS? I have no information in this problem, in the entire dictation, the entire problem when we go through. So we don't have any information about the MS, and we shall assume it as 0. So we shall assume it as 0. Or even if you assume some value and then proceed, then also absolutely no problem. Okay, so all the data we have written in, and now I hope we'll be able to start. Okay, so now what are the things? One is minimum position, the other one is maximum position, and the other one is some other position. So I have three cases: minimum position, maximum position, and some other position. That is when R is equal to 90 mm. Of course, that is the second case. So to get this, I have to go through what is called as minimum position analysis, then maximum position analysis. Okay, then probably I will be able to find out one of them. So now first I shall do it. What is the first one? I shall try to answer. In that, the first case, minimum position. I shall call it as minimum position. The sleeve is at its lowest position. Okay, let me make this sketch. So this is the spindle axis. Then immediate thing is what is the position of the fulcrum. This is what I call it as C, and C is what is how much? This is 80 mm. I shall write it straight away, 80 mm. Okay, then the radius of rotation of the ball. So what is R minimum? R minimum is 75 mm. Okay, R minimum. So I shall mark what is called as 75 mm. 75 mm. This is the line in which the balls are revolving. And I know what is this distance, and therefore, so the ball will be on this line and join here. And this is the ball arm. And how much is this distance? This is 100. Ball arm. And perpendicular to this ball arm, you have what is called as the sleeve arm. And that distance is 50 mm. Okay, everything is right, fine. Okay, then what are the forces that are acting? I have what is called as, okay, I shall go, I have the weight of the ball, since I have to neglect the obliquity, due to the obliquity effect, neglect the moment. This thing, therefore, you don't have to write down. This is MB, so this is omega minimum square R minimum. This is the force. Okay, then what is the force here? The weight of the sleeve is 0, therefore ms into g is not there. I have what is called as only S minimum. S minimum divided by 2. Okay, only this. So though I have force here, the weight, and because of this I am not considering it, and write down what is the moment equation. So it is quite simple. It is mb omega minimum square into r minimum. This multiplied by b. This multiplied by b is equal to S minimum by 2 multiplied by a. Okay, now while substituting, you have to be very careful. If you substitute here 1 millimeter and here 1 millimeter, okay, this side millimeter cancels. You can substitute b in millimeter, a in millimeter, absolutely no problem. And mb is in kg, omega minimum, that is in so many radians per second, r minimum value. You cannot substitute this in millimeter and call this spring force S minimum in Newton. Okay, you can't do that. If you substitute r minimum also in millimeter, b in millimeter, a in millimeter, then you cannot call S minimum in terms of Newton. You can write b in millimeter, a in millimeter. Fine, no problem. Millimeter cancel, but R has to be in meters. Or to avoid any confusion, make it a rule to substitute whenever you come across the length dimension, substitute in terms of meters only. Then absolutely no problem. I shall make one substitution for you to demonstrate. This is equal to 1.4 and omega minimum. I don't have that value, you have it, and square of that. This R minimum is 75 into 10 raised to minus 3 multiplied by B. This is 100 into 10 raised to minus 3 is equal to S minimum by 2 multiplied by A, that is equal to 50 into 10 raised to minus 3. Okay, all the values I have substituted, everything is known, and the only unknown is S minimum, that you find out. And that is equal to so many newtons. So this is the result from the analysis of the Hartnell governor when the sleeve is at its bottommost position, lowest position, minimum position. I hope you understand. Okay, we are able to find out S minimum. Okay, so now let me go to what is called as the second part, the first one itself, and now what I do is for maximum position. Okay, I shall run this and then go for the maximum position, which is the second case. Okay, this is number 1 and B part, and this is maximum position. That means the balls are revolving at R max. Okay, let me go for it now. This is the spindle axis. So unlike in photo governor, I am not using any ready-made formula. Every analysis, every situation, every position of the sleeve, I shall apply the method what I have taught you. Okay, so this is the spindle axis. Now immediate thing is what is called as, what is this? This we call it as the fulcrum, and this distance is C, and C we know that it is 80 mm. Okay, now immediate thing is what is the R max? Where are the balls, at what radius they are revolving? They are revolving at 120 1.5. That means beyond 80. So somewhere here, this is the position of, or this is the line in which the balls are going to be revolved, and this distance is 112.5. 112.5. Okay, so now this is where you have the ball, and this distance is only 100. This distance, and perpendicular to it is this sleeve arm. This is 50. Okay, now straight away let me go for the question. This is mv into omega max square into r max. I know mv, I know omega max, I know r max. No? Do we know r max? Yes, 1.5. Everything is known. Okay, now what are the forces that are acting at the sleeve? What are the forces that are acting at the sleeve? Okay, let me show it here. This is S max divided by 2. The sleeve is at its maximum position, that is why I am calling the spring force, corresponding spring force as S max. Okay, S max by 2. Okay, now straight away the moment equation, quite simple. S max by 2, S max by 2 multiplied by 50 into 10 raised to minus 3 is equal to 1.4 mv omega max value you know, square of it, r max again value 0.5 into 10 raised to minus 3, this is r max, multiplied by the moment arm, that is equal to 100 into 10 raised to minus 3. So all the values here except S max are known, and S max is the only unknown, and find it out. S max is so many newtons, because everything, this is mv omega square r also is in meters, therefore the force what you get is in terms of newtons. So you know S max. Okay, you know S max, you know S minimum, and if you know what is the sleeve displacement between the minimum position and the maximum position, you can easily find out what is the stiffness. Okay, so now quite simple. So what will be the displacement? What will be the displacement of the sleeve from the minimum position to maximum position? Say I just draw here, the minimum position was something like this. This was the ball, and this was the sleeve, and this was the Hartnell. Just to show you. This is the minimum position. For maximum position, it is something like this. This is the maximum position. And I want to know what is this displacement. So in general I call it as X, sleeve displacement between minimum to maximum. This is. And what is this distance? This distance I know that it is, say let me assume that this is the spindle axis. Spindle axis. This distance is R max, this distance is R minimum, and what is this value? This value is, what is that? R max minus R minimum. So here, so you have a triangle due to one arm, and you have another triangle due to another arm of the bell crank. And you know that both triangles are similar to each other. So therefore X min max divided by one of the side of the triangle, that is equal to A. This is equal to, how much is this? This is R max minus R minimum divided by one of the side of the triangle, that is equal to D. Okay? This is the only unknown, this is known, this is known, this is known, this is known, and therefore what we can find out, X min max is equal to so many. Okay, if all the things, this is in millimeter, millimeter minus millimeter, this will be millimeter, this also millimeter, cancels, millimeter cancels. If you substitute A also in millimeter, then you also get it in millimeter. It may be millimeter or it may be meters, depending upon what you substitute, you are going to get it. So now you know the sleeve displacement, the maximum sleeve displacement, you know S minimum, you know S maximum. what is the relationship between S maximum, S minimum, etc.? S max is equal to S minimum. S max is equal to S minimum more than S minimum plus Ka multiplied by X min max. I hope you understand. X min max is the displacement compression of the spring, and therefore that compression multiplied by stiffness, okay, that will give you the force in Newton. This is in Newton, this is in Newton. Please remember here X min max, if you substitute in millimeter, then you get K value in Newton per millimeter. Otherwise, don't worry about it, don't go for millimeter at all and substitute everything in meters, and then you will get K, so many Newton per meter. This you can easily convert it into Newton per millimeter by substituting meter. 1 meter is 1000. So divide this value by 1000, you will get Newton per millimeter. Quite simple. And therefore, this is how you can find out. This is the first part. I hope it's clear. Any doubt? Okay, let me know your doubt if at all they exist. Okay, and I wish if you have doubt, then probably you can go through my explanation once again, and I hope you will be able to complete the problem. Okay, now I have the second part of the thing what is asked in the problem. Please remember, now I know the value of K. You know it, I don't know the exact value, but I have demonstrated you how to find out the K value, and remember K value is known to me. So that I will be using for my second thing what is asked in the problem. Okay, so now coming to the second part. Second part. So R is equal to 90 mm. And what is omega? Now, this is what is asked. Okay, again go through basics. This is the spindle axis. Spindle axis. You have what is called as, what is this? Fulcrum. Okay, how much is this distance? I know that this is 80. Yeah, this is 80. And the radius of rotation is 90. Therefore, the ball is this side. The ball is this side. And maybe you can draw a line. So this is 90. This is 90 mm, and somewhere here this is the ball, and this is your bola, and this is your sleeve. So where was your minimum position? I just draw it. Minimum position was something like this, minimum position, and this distance. Okay, I require this. This is what I call it as X minimum to 1. Okay, minimum to position 1 now. Okay, minimum, from minimum to position 1. We had called it as X min 1 little earlier. We had while discussing. It doesn't matter. From this position to this position, how much is the displacement? Okay, so now quite simple. So I know. The first thing before I really start, I shall find out what is X min 1, min to position 1, or min to the position, the present position. X minimum to present, I shall call it X minimum to present. What is the present position of the sleeve? Okay, divided by A. So make use of this. Is what is X min to present position divided by this arm, that is A, is equal to what is this value. This is okay R present, that is 90, minus R minimum. What is R minimum? R minimum is 75. Yes, 75. Please remember 90 minus 75. If you are not happy, you want it in meters, you can have 10 raised to minus 3 divided by A. Sorry, not A, B. That is B is 100. 100 into 10 raised to minus 3. Say A value also, I shall write it down. This is 50 into 10 raised to minus 3. So from this, what you get? X minimum to present position. So how much it is? This is in meters, this is in meters, this is in meters, this also is going to be in meters. So this is what we have found out. How much sleeve has moved from the minimum position to the present position of the sleeve? That's what we are able to find out. Now, before I write down the equation, I shall also call the present spring force as S. S is the spring force. Okay? So how much is this? So do you agree? Is it more than minimum, S minimum, or is it less than S minimum? So when it was here, the spring force was S minimum. The sleeve has moved up. The sleeve has moved up. That means the spring has been, the top end of the spring is fixed. It can't go up. Only the bottom sleeve has gone up. That means the spring has been further compressed. When the spring is further compressed, that force is definitely more than the minimum position. S is more than S minimum. So S minimum plus how much? That is K, which we have found out, Newton per meter, multiplied by X min to present. X minimum to present position. This is in Newton per meter. Sorry, this is meters. This is Newton per meters. Therefore, this also will be Newton. And S minimum, you already know it. We have found out. This also is in newtons. And therefore, you find this out. This is so many newtons. Okay. So I know what is the spring force. I have a spring force S divided by 2. Then what is the force, or what is the centrifugal force? MB. Okay, MB. Let me write it as MB only. You can substitute. Then let me assume the speed as omega square. You know MB. Please remember into R. You know R also. Okay, this is the force. Okay, and I am supposed to neglect the obliquity effect. Therefore, I don't consider the weight of the ball. And my symbol now it is yes. MB into omega square into R multiplied by B is equal to S by 2 multiplied by A. So A is 50 mm, 50 into 10 raised to minus 3. S is so many newtons, which we know it, we have found it out. This B is 100 into 10 raised to minus 3. I know R 90 into 10 raised to minus 3. Omega square is unknown. MB is 1.4 kg. All the things are known except omega. So from this you find out what is omega square. Then take the square root and you find out omega. So many radians per second. And from this omega, I wish you to find out m in RPM. So therefore, this is the speed of the governor at when the speed of the governor or speed of rotation of the walls when the radius of rotation is 90 mm. Okay, though it may take little more time because when you are doing it first time, but then you don't have to explain it to anybody else, and if you have to carry on your own, I don't think it will take more than 10 or 12 marks, and the number of marks allotted for this question happen to be 12 marks. Okay, and therefore, though I wanted to solve one more problem, maybe I shall solve. I don't have to explain anything and straight away solving problems. Maybe 2 or 3 problems I will be able to solve it in my next class. Okay, all the best. Please practice.